clouds are absolutely critical to the Earth's climate system, along with the particles that form those clouds. And the reason is that we actually understand the greenhouse gases rather well. So for over 100 years now, we've known the radiative effect of, say, adding carbon dioxide to the atmosphere. So carbon dioxide acts as a blanket, and it traps some of the outgoing heat that's trying to get away from the Earth's surface. And we're actually very happy there's carbon dioxide in the atmosphere, because otherwise the atmosphere, the planet would be too cold and life wouldn't exist. But the problem is that we're adding CO2 to the atmosphere and thereby warming up the planet beyond where we've sort of evolved to be at the temperature that we're sort of used to, not only us, but the other life forms on Earth. So we know that we're adding carbon dioxide to the atmosphere. We know that this is having a warming effect, and this was all worked out. All of the radiative transfer was worked out over 100 years ago. And most people understand that. This is sort of a well-understood part of the Earth system, and most people understand that adding CO2 has this effect that we call global warming. What a lot of folks don't know about is the role of particles and the role of clouds. So human activities at the same time as putting out CO2 are also putting particles into the Earth system. And these can be the particles that you see spewing out of a smokestack or coming out of the dirty truck in front of you as you're commuting to work. And it turns out that those particles, for the most part, are scattering sunlight back into space before it makes it to the ground. And you can most easily think about this as being in a city on a smoggy day or a hazy day, and you get this very diffuse light. It's looking at the sun is like looking through frosted glass in a bathroom. And you can tell that not all of that sunlight is making it to you. And so what this is doing is sending some of that sunlight back into space that would have otherwise made it to the surface to warm the surface. Another thing that we explore in lab is that these particles act as the seeds that cloud droplets and cloud ice crystals form on. And what it means is that as we as humans put more and more particles into the Earth system, we're changing the properties of the clouds in the Earth's environment. We're making more clouds, we're putting them in different places, different altitudes, and different location because of the particles that we're putting in. And if you've ever been out on a sunny day versus a day that has clouds, you know that the cloud is going to intercept some of that sunlight coming in. It's going to scatter it back into space. Clouds are in general sort of a white, a high albedo, we say, effect. And so they're going to send that sunlight back into space and not allow it to the surface of the planet. So what does this mean for the climate system? It means that we're doing two things. We're doing the well-known thing of increasing temperature by putting carbon dioxide, greenhouse gases into the Earth system, warming the planet up. But then at the same time, we're taking some of the sunlight out of the system because these particles we're putting in are sending solar rays back into space, and the clouds that they're forming are also sending solar rays back. Where does it end up? Well, it ends up that the greenhouse gases are winning. The effect from the greenhouse gases is larger than the effect from the particles and from the clouds by several times. And so we have a warming effect, but we're not realizing all of the potential warming we could have because the particles and the clouds are keeping that down. It's minimizing the effect. What's even more important for us as scientists is that we've known about the carbon dioxide, the greenhouse gas effect, for a long amount of time. We've worked out all of the physics involved in that. We understand the emissions of this material to the atmosphere really well. We haven't had as much time understanding the cloud and aerosol system, so they're much, much more uncertain. So for example, there's this Intergovernmental Panel on Climate Change report that every 4 or 5 years assesses the state of the Earth's climate and how humans are impacting it. And one of the things that they've noted is that although the aerosol and cloud effects are smaller than the greenhouse gas effects, they're about 4 times as uncertain. So what this means is when we add up all of the human effects on the Earth system, our certainty of that is really set by lack of understanding of the aerosol and cloud effects. Until we understand aerosols and clouds, we're not going to figure out the climate system on its own. Particles themselves are rather complex in the Earth system because they're very, very heterogeneous. It's a term that we use to say that they're not the same depending on where you are in time and in space and in altitude. They change on a daily basis depending on what's being produced. You can think about this in the case of a wildfire producing a smoke cloud. One day the fire hasn't started, so there's none of these particles. A few days later, the fire's in full swing and you're getting a ton of particles. And then maybe the fire's been put out and you've got this smoldering going on with a little bit of particles being produced. That's just one simple example. But if you think of the Earth's atmosphere as a whole, particles are very heterogeneous. They may appear in one location, the wind may blow them out of the way, they may be produced at one point in time and not another point in time. Even more complicated is that different particles have different effects on the Earth's system. We've talked about clouds a little bit. They may be very good at forming clouds, or they may have no effect on cloud formation. And so that's one effect they can have. The other is that they have certain properties in terms of interacting with solar radiation. And what I mean by this is that you can think of particles like sulfate particles that might come out of a smokestack, organic particles that might come out of a forest setting. And those tend to be very good at scattering solar radiation. They're very good at offsetting this climate effect by sending solar rays back to space. There are other types of particles, things that we call black carbon, sometimes that are called soot. And this is the material that would come out of that dirty truck that's in front of you as you're commuting to work. And as the name implies, they're very dark, they're very absorbing. They actually trap that solar energy. They're very good at intercepting it and holding it in the Earth system. So they're actually a warming agent. They're like a greenhouse gas. It turns out that there's a lot more of these sulfate and organic particles that are scattering radiation back into space than there are soot particles that are absorbing it. So aerosols are a net cooling effect, but there are certain particles that act as warming agents, and working out that exact balance is one of the things that we have to do as climate scientists to figure out what the aerosol effect is. We're going to be running an experiment to show how critical small particles, aerosols, in the atmosphere are for the formation of clouds. To demonstrate that, we're going to make a cloud, and we're going to do it in this little jar right here. So to get started, this is going to mimic a cloud that's going to form over a body of water like an ocean, so that you can see the bottom of this has a bit of water in it. So you could pretend that we're going to make a cloud, say, over the ocean off of the coast of Boston or something like that. Normally, clouds form by convective activity. The surface of the Earth heats up, the air is somewhat warmer, and then it moves upward in the atmosphere. And as it does that, the relative humidity increases, the temperature decreases, you hit 100% relative humidity, and your cloud forms. Unfortunately, I am not tall enough to lift this quickly enough to get a cloud to form in it. So instead, what we're going to use is a pump to drop the pressure in this and mimic that cloud moving up, or that air moving up and forming the cloud in the atmosphere. And you can tell the pump is on because when I put my finger over this little filter right here, you'll hear a slight sucking noise. And that's the pressure in the jar dropping, which is going to be akin to this moving up in the atmosphere. And I can hold my finger over this for quite a bit of time, and you won't see anything happen in the jar inside. There's no cloud forming. And the reason that there's no cloud forming is that this little piece right here is actually a filter. So it's taking all of the particles out of the atmosphere before they make it into the jar. So this jar right now is only air. There's no particulate matter in it whatsoever. As the pressure drops, the relative humidity is going up quite a ways. It probably is reaching 110, 120% relative humidity, a humidity that you would never hear on the nightly news, and yet there's no cloud that's forming. So what we have to do is introduce particles into this jar to get the cloud to form. We're going to do this with a common household match, and you can imagine that this is going to mimic a process like burning down a forest, wildfires, that's going to add particles to the atmosphere. So we first light the match, and then to get the particles to form, you'll see the smoke come off in just a moment. So here's the smoke. We let it into the jar. The jar now has particles inside of it, and when we do that, the cloud can form on those particles that we've put into it. We'll let the relative humidity go down, and the cloud goes away. There's still some particles in there, though, and so another cloud will form on the particles that are left over. We can let some more air into the jar, and yet more particles will form on a cloud. You'll notice that the cloud becomes thinner and thinner each time because we're removing particles every time I open this up and they're pumped away. So obviously this is not a high-tech cloud chamber. This is not something that we can use to produce laboratory quality data. Instead, what you see behind you is one of our high-tech chambers. This is something where we have very precise control over temperature and relative humidity. And this instrument is able to figure out the size of the cloud droplets that are being produced and the number that are being produced. We can also add specific particles to it. For example, if we're interested in biomass burning, we don't have to use a match. We can put particles in there that have been burned from material that we're interested in. Or we might be interested, for example, in a dust storm. And we're able to put mineral dust particles into this and see what their cloud nucleating potential is. And so instead of having the water in the bottom of the jar, the water is actually in one of these jars, and it's constantly fed through this unit. And what you can see on the screen right here are the number of droplets being formed versus the cloud particle size in this case. So this is how many droplets are being made, and this is how big those droplets are. And right now, we're just simply looking at the number of cloud droplets that are being formed in the ambient atmosphere. So how many potential cloud particles could form in the environment that we're living in right now. In the background behind you is a homemade cloud chamber, something that we use for looking at the formation of ice clouds. And that's maybe not surprising by the amount of insulation and duct tape that's on it. But we can build something like this and make it specifically for our use. There's one particular cloud type that we're really interested in, which are cirrus clouds. People know of these as being the very thin, wispy clouds that you see, especially on a clear day. They're composed entirely of ice, and they're existing high in the atmosphere, so many miles high. You know, it's sort of the type of cloud that you pass through when you're on a jet airliner. We're interested in them because they are among the most uncertain parts of the climate system. So I've already said that aerosols and clouds are uncertain. Within aerosols and clouds, one of the most uncertain things is the formation of these high-altitude cirrus clouds. They're very important for climate. They tend to be the first clouds that solar radiation sees on its way into the atmosphere. It means they're the first thing that can scatter radiation out of the Earth system. Because they're very high, they're also the last thing that the heat from the Earth trying to get into space sees. So they're the last thing that can sort of intercept that radiation and perhaps trap it, send it back towards the planet. They're actually so uncertain that there's debate about what forcing they have. And what I mean by that is that there's debate about, are they a warming agent for the planet or are they a cooling agent? Which of the things, the interception of radiation or the trapping of Earth's radiation, is winning out? And almost certainly that sign, the warming or cooling, changes depending on where these clouds are, where they are in the atmosphere, how high they are. And all of these things are changing as humans change the particles that they're forming on. And we're in particular very interested in some of the minor components of the atmosphere, things like heavy metals, lead that comes out of things in the past came out of tetraethyl lead that was used in gasoline. Now it's increasingly seen as a byproduct of coal combustion. So there's a bit of lead that's emitted when you burn coal, and that finds its way into these particles. And that lead is one of the key determinants in if something nucleates ice well, if it forms these ice crystals that cirrus clouds form on, or if it doesn't form the cloud. And so we're keenly interested in how human impacts, how small things, small trace amounts of material that humans emit into the atmosphere can have on a cloud formation event or the lack of a formation event, which is this huge lever arm in the climate system. So another reason that cirrus clouds are so important is that they cover a huge fraction of the globe. So at any one time, it's thought that they cover maybe a third of the globe, maybe even more than that. And we don't tend to think about them because they're so high in the atmosphere that if there's a lower cloud layer, they're invisible to us. They're also very thin. Some of them are called subvisible, and as the name implies, we can't even see them. They're so thin that we can look through them, but we can see them with space-based instruments like satellites. To do some of our measurements, we have to use rather exotic platforms. So one of the things that we use is a NASA research aircraft. It's a WB-57. It's actually an old Air Force bomber and reconnaissance aircraft that was retasked by NASA to do studies in cirrus clouds because it can get so high in the atmosphere and then stay there for a significant amount of time to do these measurements. Okay. One of the things that's critical to understanding the Earth's atmosphere is what we call the mixing state of particles. Understanding how one particle is different from another, how a special particle is able to, for example, nucleate a cloud, whereas another particle that's very closely related isn't able to. We have a couple of single particle mass spectrometers. And so what these are able to do is understand the chemical composition of particles on a single particle basis. And so we use technology like this where we bring particles in one at a time. We strike them with a laser, and that laser is powerful enough that it ablates the particle. It essentially burns the material off, and it creates ions. And then we manipulate those ions within an electrical field, and that allows us to say what the mass of each of those ions is, which gives us the chemical composition of the particle. It tells us, is it mineral dust? But not only that, what type of mineral dust is it? Is it biomass burning? But not only that, what's associated with the biomass burning? What was the type of material that burned to create that particle? This one you can see is constructed to take to remote field sites and to put on platforms like aircraft. This one is. We do have a custom version of this that lives at the National Oceanic and Atmospheric Administration that was specifically built, the principal investigator is Dan Murphy, and it was specifically built to go on research aircraft. This one is of a company that has built a single particle mass spectrometer. So one thing that you can see is that it's somewhat smaller than the custom instrument, and we sacrifice a bit of precision to do that. So it's not specially built for our questions, but it's much more in general useful. And usually these are much more useful to somebody that hasn't been working on an instrument like this for a number of years. They're much more plug and play. We do two things in this group. So one of the things that we do is development of instruments, custom instruments for what we need to do. So this would be an example of a custom single particle mass spectrometer, something that's home built for a specific task. And we've modified this one and used it largely for doing cloud studies. So it's very precise. It has very good resolution. Right now, we're trying to get funds to build a small version of this instrument. These big research aircraft are going away, so we want to build this and put it on a UAV, which is this new generation of technology. We've got the new platforms. There's no money for us to build this instrument for a UAV right now. Agency after agency says it's not in our budget right now. This experiment is called an electrodynamic balance. And in a way, I like to call it our anti-gravity chamber. So we put a single particle, so one particle at a time is trapped in here, and it has a small electrical charge on it. So say that it has one positive charge on it. We have an electrode on the bottom that's positive, an electrode on the top that's negative, and what happens is that particle experiences a force upward in the electrical field, and we very precisely tune it to offset gravity. So the particle is perfectly suspended in the electrical field versus gravity, and it's held there. The record that we know of is that there was a particle that was trapped in this for something like 3 weeks for experiments to be performed on, so it was sort of levitated anti-gravity for 3 weeks. And we're actually using this to understand cloud formation under very radical conditions, very low temperature conditions, for example, clouds that would form around other planets like Mars, Venus, exoplanets, and so on. We can do in a chamber like this. The questions that often comes up when you talk about clouds and climate change is, can you use clouds to offset climate change? So as soon as you say that particles in clouds are a cooling effect and they offset some of the global warming from greenhouse gases, it's sort of natural to say, well, why don't we make more particles and more clouds? And there's actually a lot of reasons why we should not be doing that. When it comes to making more particles, one of the things that we found out over recent years is that particles have an incredible health risk associated with them. So a lot of childhood asthma, a lot of cardiopulmonary diseases are completely correlated with the amount of particles that somebody inhales over their lifetime. So simply making more particles doesn't really make sense because we would have an incredible loss of human life. The next step that people go to is, well, maybe we could tailor make clouds and put them in some part of the atmosphere to send solar energy back into space before it makes it to the surface of the planet. And there's actually quite a following of this. It's sometimes called geoengineering. This had sort of a rather bad connotation of manipulating the climate system, and so it's been resurrected as something called solar radiation management, meaning attempting to control the sun's rays coming to the planet. And unfortunately, the people that are proponents of this don't mention a lot of the side effects or the things that aren't addressed by this. So for example, if you put particles or clouds high in the atmosphere, we already know from things like volcanic eruptions that this has an incredible bad impact on atmospheric ozone. For example, they represent sites on which ozone loss can take place. And we know after volcanic eruptions that ozone goes down as a result of having those particles in the atmosphere. And so this would be a side effect of trying to put particles and clouds into the atmosphere to offset solar radiation. And it's certainly something that we've only now begun to recover from the CFCs, the chlorofluorocarbons that were depleting ozone in the 1980s and 90s. So that would be one side effect. Another is that by putting particles and clouds into the atmosphere, you're not addressing the problem of rising CO2. So that warming is still taking place in the atmosphere. Carbon dioxide is still building up in the atmosphere, and so you're not addressing anything like the ocean acidification issues that go along with having this increase in CO2. And so that's something that's very often not talked about. From my standpoint as somebody that works with particles and clouds, the thing that doesn't make sense to me, the reason that this is so illogical to me, is that we've already talked about how uncertain the effect of particles and clouds is. If you go to these things like the IPCC report, which say that particles and clouds represent 4 or more times the uncertainty of greenhouse gases, the solution of somehow tweaking particles and clouds to offset greenhouse gases is sort of like using the coarse knob on an old stereo system to tune something as opposed to the fine knob. We know the effect of CO2 very well. We understand its role in the climate system. That's the knob that you want to tune out a temperature issue. You don't want to use the thing that you don't yet understand to do that. So simply saying that it has a negative effect, that it has a cooling effect, isn't enough. You have to also ask yourself, do we understand it well enough that we could actually get some kind of a measurable effect of the magnitude that we want? And the simple answer to that right now is no. The reason that we're doing so much work in this part of the field is because we don't understand it. And so it doesn't represent a mechanism that we can simply use to tune climate to our liking.
The reason that we're in Germany is that the Karlsruhe Institute of Technology has some of the world's leading chambers for the study of aerosol particles and clouds. When you go into the environment, one of the problems is that if you find a cloud that you want to sample, or you find particulate matter that you want to sample, the atmosphere has already done something to that. In other words, it has already reached a certain relative humidity and a certain temperature, and the cloud that you're trying to study is already formed. The reason that we like doing research at the Karlsruhe Institute of Technology is that we have precise control over temperature and relative humidity, as well as the particles that we're studying. We can collect samples, for example, of mineral dust or soils from around the planet. We can use engines to produce black carbon particles, the types of things that come out of smokestacks or trucks, and we can put those into the chamber, put them under a precise set of conditions, and look at them. One of the instruments that we've brought from MIT here to do research is what I'm standing in front of. This is a particle mass spectrometer. We call it particle analysis by laser mass spectrometry, or PALMS for short. The way that this instrument works is that we use an inlet to bring particles in, a single particle, one at a time, and these particles are very small. They can be, for example, on average about 1/50th the diameter of a human hair. We bring those particles in, and the instrument has to know that there's something there to detect. We do that by using a laser beam. As the particle passes through the laser beam, it scatters light. You can think of this just like being in a dusty room when sunlight's coming in. You can see the dust in the air by the particles reflecting some sunlight, and you see the little twinkling. That same thing happens here. We don't use sunlight, we use a laser. So this is very much akin to something like a laser pointer that you might see when somebody's teaching a class. Once we know there's a particle there to detect, a second type of laser is activated, the one on this far corner in this box over here. That's called an excimer laser, and it's the same type of laser that's used for LASIK eye surgery. So this is a laser that would normally be used to shape the lens in your eye. Instead, we strike the particle with it, but it does exactly the same thing. When it strikes the particle, just like striking the lens in your eye, it heats it up. It essentially burns the material apart, and it creates ions. So ions are the fragments of the particle that we want to study, except they now have an electrical charge on them. We use that charge to our advantage so that we extract the ions, either the positives or the negatives, and they sort of pass through a detection apparatus here, and that tells us what the chemical composition of the particles is, a single particle at a time. So again, just to repeat, these are very small particles. You can't even see them in the atmosphere. They're about 1/50th the size of a human hair. And we yet get the entire chemical composition from a particle with this type of instrument one at a time. So traditionally, we bring this particle out into the environment. We use it to tell us what the particulate matter in the environment is, what's there. We also use it to tell us what the seeds are that clouds have formed on. That's great in the environment. We use it here at the Karlsruhe Institute of Technology because we have such precise control over the formation of these clouds that we're studying, and we can use any number of different particles that are collected from the surface of the Earth. We then use this particle detector as a diagnostic to tell us exactly what we're looking at. What are the special components of these particles that lead to cloud formation, that lead to their being able to affect the Earth's climate?
This is one of the instruments that we brought with us. This is a laptop from a company called Aerosol. It is a single particle mass spectrometer, and what this means is that it samples single particles in a range of sizes from a sub-micron to around a micron, maybe up to 10 microns. It samples them through this inlet, and then once it passes a laser beam through the back, another laser beam extracts the ions from the particle, and that in this way we can get a complete chemical composition of every single particle that it samples. The way this works is that the particles come in here, they cross a laser beam here, a triggering laser beam here, and then this laser, which is at 193 nanometers, fires, and the UV radiation is enough to ionize the particle, and once the particle is broken up into the ions, the ions are sampled with a mass spectrometer shown here. The mass spectrometer measures the mass of ions liberated from the particle by imparting a kinetic energy to them, and then measuring the kinetic energy. So here is, this instrument is actually sampling right now. Mass spectrum, a positive mass spectrum and a negative mass spectrum. The peaks right here represent the ions of a certain mass. These particles were broken up into those ions, and then we see an intensity versus a mass to charge ratio graph. And as I said, these particles are primarily made out of carbon, and this actually shows up very clearly on the spectrum. Instruments are of a great value in our research because they allow us to analyze single particles that have atmospheric relevance, analyze their chemical composition. And primarily here at AIDA, we're interested in whether or not such particles are good ice nuclei and whether or not they can nucleate clouds in the atmosphere. This instrument is largely under construction right now and under improvement, but we hope that with continued efforts, it can be of a great value in ice nucleation research.
I'm Ottmar. I'm working here at KIT with the AIDA facility, which is this big cloud chamber where I can simulate processes of tropospheric clouds or atmospheric clouds. So here we are in the control room where we can have control of the facility. You see here some data like the temperature and the pressure. So we lower the pressure in our experiments to simulate air parcels lifted up in the atmosphere, and in these air parcels clouds form, and these cloud formation we simulate in the AIDA chamber. And on the other screens we have control of those pressure systems and gas systems which we need to do our experiments. In November we did some very interesting experiments together with our friends from the United States and also from Europe. So that was just aimed at looking into single aerosol particles and see how they are made of or what they are made of, and which sorts of the aerosols would be active to make icing clouds. And that was investigated here in experiments at the AIDA facility, and our friends and colleagues brought these fantastic new instruments for single particle measurements here to the AIDA facility, where we work together to find out which of those, as I said, particles are active in clouds to make ice, and those ice crystals then later on induce precipitation and so forth.